sometimes visualize maybe a couple.
Okay, folks, let's go ahead and start. Any questions? Yes?
Sir, in the boost converter, there's this graph for VC. Could you please kindly explain that once?
Okay, you mean the ripple? Okay, the question is about the ripple of the capacitor voltage in the boost converter, right?
It's the voltage across the boost converter. There's this graph like this and this.
Okay, let me see. All right, let's see if we can find it. This one, something like this, you mean? But for the boost?
No.
Is it the voltage of the cap or?
The voltage of the cap.
Okay, the voltage of the cap. Okay, this is the buck boost one. Let's find the boost one. All right, so this one over here.
Yes.
Okay. So, so what's happening here is, if you look at the current of the cap. Let's see if I can erase things over here. All right. So if you look at the current of the capacitor, when the switch is on, the diode is off, and therefore what's happening is this cap is being charged over here. And because we are assuming the voltage of this cap is constant or has a large DC component, this current is almost constant, approximated over here. Then in the second mode, this diode is on, so basically we will have some positive current charging the cap. So on average, the current of the cap should be 0. That means the capacitor is neither getting charged nor discharged. Okay. So if we have this waveform for the cap current, we should integrate this to be able to find the capacitor voltage. Okay. We already know that the cap voltage has a very major DC component. So there is like a, we are over here, we are only focusing on the ripple aspect of that. So initially you can argue that the cap is being discharged with a constant current, therefore the voltage of the cap is going to go down linearly. Just integration of a straight line, a flat line, is a constant value is just a decline. Then over here the current of the cap is positive, so the indication is the voltage of the cap is going to rise, and because it's a straight line, when you integrate that, you're going to get like a quadratic kind of a, you know, second order kind of a form. Okay, so that's how it is. Now if you simulate this, it may be a little bit different. What I was trying to do last time in simulation, it didn't look like this. The problem is the capacitor that I use in the simulation is very large. So if you make that cap a little smaller, you're going to see a pattern like this. What we saw in simulation was pretty much like a triangular waveform, pretty much like that. That's because the cap was too large. If you make it smaller, you're going to see this behavior over there as well. All right, any other questions? Okay. So a few announcements. One of them is about Blackboard. So when I tell you guys that I'm posting something on Blackboard, pretty much everything is, you know, posted under content. So you have to just click on content. And I don't know why it's not doing it. Anyway, let me just, okay. Somehow the content is not working, and I don't know really why. Anyway, so, okay. Okay, here it is. So we have the schedule, the syllabus of the course. The schedule of the course changes, and I actually tell you when was the last time I've uploaded this thing or updated this thing. And the grades are here. The Excel file reflects all of your grades. This is how you can calculate your grade. Just an equation. This is all of my class notes and in PDF scanned. And these are the class notes that we have in OneNote. So if you want to open them, you can do it. And the sample homework assignments are here. Any MathCAD file that I use in class, I've used this one when we were talking about rectifiers, are here. And this folder over here, DC-DC converter simulation models, I have a model for Buck, a Plex model for Buck, and also the boost model that we discussed last time. This one is also here as well. So if you want to play around, you can do that. And as we go further in, for instance, isolated boost converter, we had a question last semester about it, so I have actually found a paper about that. Then later we're going to talk about modeling and controller stuff. So these are mostly futuristic, the stuff that we haven't really covered yet. All right. And by the way, you guys know that because some students have asked me questions, so I just wanted to make this clear that you guys know that these lectures are being recorded and are available to you guys. So if you miss a class, you can just go to the distance education website and watch the lecture basically up until the end of the semester. The other announcement that I have is about the Granger Awards. This only applies to U.S. citizens. So if you are a U.S. citizen in this class, undergrad or master's or PhD, you are eligible to apply. In order to find more information, go to power.msd.edu, which is the website for the Power Group. Go look at this under awards and scholarships, and you can see this Granger Power Engineering Student Award. The application deadline is January 15th, 2014. So basically, the idea is to encourage students to take more power courses. For instance, you are an undergrad in this class, you are a U.S. citizen. All of our undergrads in this department have to take one power elective, which is 205 or 207. So let's say you have already taken that. You are in 353 now, so if you take one extra power course next semester, you're eligible to apply. This is the list of the courses. You can see power electronics is in the list. 205 and 207 are in the list. So for instance, next semester you realize that, yeah, if you have taken 205, you can take also 207 to be eligible to apply. So the requirement is to take 3 out of this list of power courses, or 2 power courses and doing a senior design project under the supervision of a power professor. Now, who are the power professors? Here they are. If you look at people, you see, a list of good-looking people over here. So Dr. Crow, Dr. Kimball, myself, and Dr. Shamsi. So you can do that. If you are a master's student and a U.S. citizen, the requirement is your basically research or your thesis should be supervised by one of the power people. Okay, so if you feel like you are eligible, you are close to eligibility, I guess sometimes what it takes is just take 1 extra power course for the next semester, especially now that the registration is coming up. And if you are graduating this semester, or if you are graduating next semester, and there are some students who graduated last summer, they are all eligible to apply. All right, so we usually award about 11, I think, students. So 11, and everybody gets $5,000 check, a $5,000 check. All right. So last time we pretty much wrapped up our discussion on the classic DC to DC converters. And by the way, regarding your quiz for next week on Tuesday, this chapter, I guess 6, is going to be covered in the quiz. The topics are, for instance, the buck, the boost, and the buck boost converters operating under continuous conduction mode and discontinuous conduction mode. Now what we are going to do today is we are going to move on to the next chapter, and I guess this new chapter is chapter 7, which is called power supplies. And as it turns out, power supplies and DC to DC converters are basically the same thing. They're just named differently to differentiate between which one has isolation and which one does not have isolation. So we are starting this new chapter, isolated DC to DC converters. The topic is still conversion of a DC source voltage to another DC source, and but they are isolated. Okay. So when we talk about isolation, the first thing that comes to mind is a transformer. A transformer provides isolation. So one question would be, first of all, why do we need isolation? Okay. So there are several reasons for that. For instance, one reason is for safety reasons. You want to isolate one part of the circuit from the rest of the circuit, so that if there is a fault or there is a person touching something that they shouldn't be touching, the grounds are kind of separated. So that's one reason for isolation. And for this reason, there are lots of standard requirements. So if you're trying to sell a particular product, most of the times one of the requirement is that product, for instance, the power supply for your computer maybe, has to be isolated. So you should have some sort of an isolated DC-DC converter in there, or rectifier over there. So one is safety. And the other reason could be the product itself requires isolation. For instance, product is in two pieces. For instance, think about an electric toothbrush, okay? And the primary side of a transformer is in the base, and the secondary side of the transformer is the toothbrush, and they are not physically touching each other. I mean, they're not electrically touching each other. So that could be another application. And in the future, we are talking about your cell phones could be charged wirelessly, so that's another isolation, or your electric vehicles would be charged wirelessly, So those are some applications that you don't have to plug something in. As long as it's within some physical boundaries, the device is going to get charged. The other application could be you have a system, and you have, for instance, a source, and let's say this is your ground plate. Well, first of all, if you have a capacitor over here somewhere in the system, and you want to charge this capacitor, that's very easy, because right now, the way I've drawn this, the source and the cap are sharing the same ground, so all you have to do is just connect a DC to DC converter over here to charge the cap, and depending on what voltage you want on the cap and what voltage you have as your source, you may pick a buck or a boost converter. If the system looks like this, you have a source, and this is your ground plate, and then you have a cap over here. Yeah, something like that. Again, that's easy. We talked about it. The buck boost topology can do that. So if you want to transfer charge from your source and charge that cap, all you have to do is just use a buck boost topology. All right, something like this. All right. Now, what if the cap that you are trying to charge is not really connected to the ground? So you have this source, and this is your ground, and you have a cap somewhere up here, for instance. All right. Neither terminals of this cap, neither one of them is grounded. Now what are you going to do? You cannot really use a buck or a boost anymore because they are not sharing the same ground. So now you are going to have to use an isolated converter. All right. So this isolated gets these two input terminals, and also has these two, for instance, output terminals, something like that. So there are many applications where you need an isolation and an isolated converter. So isolation could be provided using, optical stuff, so opto-isolators or optocouplers. Transformers is a good example. And also you can use sometimes capacitors to isolate things with each other, but in power electronics, primarily we rely on transformers. Now that we are talking about transformers, let's kind of have a little bit of a background review about transformers, especially like in 205 electromechanics, we introduced transformers, and you have like a magnetic core over here, and then you have a bunch of primary side windings and like secondary side windings, and they are kind of linked to each other through some magnetic flux, basically, okay? So if you go back to your, for instance, class notes from electromechanics, you realize that when you want to come up with a model, an equivalent circuit model for this transformer, you have something like this. Okay, you have R1 representing the internal resistance of the copper that you have used for the primary side. You have R2 to represent the same thing, or the conduction losses on the secondary side. Then you have some parasitic, or I would say leakage inductance, which is basically taking care of the fact that not all of the flux that the primary winding is generating is linked to the secondary, flux. So for instance, you may have a flux, circulating around here, and it is not really linked to the secondary winding. So this leakage inductance is modeling that. Then you have some core losses in your iron core, basically. So RC is taking care of that. And then you have some magnetizing inductance, okay? That's the minimum amount of current that you need to apply to be able to have some flux in the system. And obviously you have a transformer, and therefore you have an ideal transformer over here as well. Okay? All right. Now, the good thing in power electronics is we don't really use all this complicated model. We just simplify it. You can say, okay, the primary side winding is ideal in the sense that it doesn't have any leakage inductance and it doesn't have any internal resistance. So you can just get rid of this. You can do the same thing for the secondary side, and you can say your core is ideal, so you want to get rid of this one, but you always keep the magnetizing inductance. Okay, a lot of times you rely on this magnetizing inductance as the inductor in your system. So if you want to simplify this model, you end up having the model that you have for your transformer is just a magnetizing inductance placed in parallel with an ideal transformer. Okay, and obviously for an ideal transformer, we already know that V1, which is the primary side voltage, over V2 is N1, the primary side number of turns, over N2 equals I2 over I1. Okay, so this is how you model that. Sometimes in some books, or some data sheets, or maybe somewhere, you may see a transformer being used in a power electronic converter, but they have not drawn this magnetizing inductance. That doesn't mean it doesn't exist. It is there, but they're just assuming that everybody knows that it is there, like a MOSFET without a diode. When you draw a MOSFET without a diode, there's always a diode there. But sometimes you don't draw it because you're assuming that everybody knows. There is a significant difference between these transformers that we used, and sometimes we just call them coupled inductors, by the way, versus the transformers that people use, for instance, in power systems. In power systems, obviously, the transformers are very large because obviously they have to process a lot of power, and the frequency of those transformers is low, like 50 hertz or 60 hertz. Because of this low frequency, they use a different, basically, magnetic material. They don't really use a magnetic material. They just use, like for instance, steel to do that. So the magnetic core is a steel, and they laminate it to reduce the losses. Over here, by the way, those transformers have very high number of turns. Like, for instance, your primary side may have 1,000 turns or 100 turns or something like that. Over here, we are talking about coupled inductors. The whole thing is very small. Like, you can actually hold it in your hand. Thank you very much. And because the frequency is high, like for instance 100 kilohertz, you have to use a different material. Like usually it's like iron powder kind of a thing, or ferromagnetic material that they can handle such high frequencies. And also the number of turns is relatively low. For instance, it could be only 10 turns on the primary side, 20 turns on the secondary side, something like that. It's not like 1,000 turns on the primary side or secondary side. So that's why you have to consider this magnetizing inductance, because this magnetizing inductance grows as you increase the number of turns. So if your number of turns in a distribution transformer is like 1,000 turns, this magnetizing inductance is a very, very large inductor, so you can neglect it. Assume that it's like an open circuit. Over here, because the number of turns is low, you cannot neglect it. It is there, and it doesn't behave more like an open circuit. It actually opens more like an inductor in the system, basically. All right, now please pay attention to these equations and these dots. It's very important to see where the dots are. And sometimes you may have actually more than two windings in your core. So let's say if I have 3 windings, so I have this magnetic core that the flux of 3 windings are linked with each other, and I have chosen these to be my dotted nodes, looking at the basically how this wiring has happened. Is it clockwise or counterclockwise, things like that. Then you can argue that if you assume all of these currents are flowing into your transformer, I1, I2, I3, okay? If you assume all of these currents are flowing into your transformer, the equation that you have to write is N1 I1 plus N2 I2 plus N3 I3 0. All right. Okay. So it's very important. The direction of current is very important. All of these currents are flowing into the dotted nodes from the outside world. And obviously the voltage is easy. I mean, always you give the positive polarity to the dotted node, the negative polarity to the undotted node. So this would be like V1, V2, V3. And you can always write V1 over N1 is the same as V2 over N2 is the same as V3 over N3. Okay. And you can say if I have the fourth winding, you can just extend this. Now, from this general equations, these are very general equations. From this comes this more specific set of equations, and this is where you only have two windings. However, the trick in the two winding is you always assume that on the primary side, the current goes into the dotted node. On the secondary side, you label I2 to coming out of the dotted node. So these directions are very, very important to remember. And that is why, basically, okay, let's say we only have two windings. This doesn't exist. This does not exist. So you basically end up having, for this particular setup that I have, you end up having I1 over I2 equals negative N2 over N1. Now, how come we have a negative sign over here? We do not have a negative sign over here because the polarity of current has changed. We are assuming that now the current is coming out of the dotted node. So these directions are very, very important. A lot of people get confused, so just keep that in mind. All right. So let's say we all have this background information and we want to analyze the first and the simplest converter that is an isolated converter. It's called a flyback converter. And the name flyback comes from where this converter was used initially. It was in older TVs, not the LCD TVs, the TVs that had these electronic tubes in them. So when the electronic beam was at the end of the basically a screen, you had to apply a large positive voltage to bring it back to the top of the screen and do the scanning again. And over there they use some sort of a flyback mechanism. So the name flyback means your beam has to fly back to the top of the page, something like that. All right. So here is the circuit diagram. So basically you have this transformer or coupled inductor, and the windings are like this. Okay, and the direction of these windings is important. I mean, I paper it doesn't matter, but if you try to build it, the where you're going to place these dots, it depends on how these windings are actually wound around the coil. But anyway, you have this coupled inductor. On the primary side, you just connect a switch and your source. On the secondary side, you place this diode and this capacitor and form a loop, and then you place your load, obviously, in parallel with your capacitor. Okay, so as you can see, the classic components appear. We have one switch, one diode, we have one capacitor. We don't see one inductor, but the magnetizing inductance of the transformer is actually our inductor. So if you draw the equivalent circuit diagram, you will end up with a schematic like this. And please pay attention, the dotted nodes are configured in this way. All right? Okay? So as you can see, we are also taking care of this magnetizing inductance. We label it to be L, M, L, inductance of magnetization. And then the rest of the system is basically the same. Now, sometimes they don't draw this magnetizing inductance, but the assumption is it's there. You shouldn't forget about it. Okay. So we are going to analyze this converter under the same assumptions that we made previously for those converters in the previous chapter. For instance, the components are ideal. We are looking at the system under steady state conditions. The output capacitor is relatively large. So the output voltage is almost DC. It's almost constant. Doesn't have a lot of ripple. And we are going to analyze the system first under continuous conduction mode and then later under discontinuous conduction mode. All right. And the modes of operation, obviously we have two modes, but the switching, which is determined by the switching pattern. So if I look at the switch gate command or whatever you name it, it's on at the beginning of the cycle until duty cycle times period. And then for the remaining of the period, it's off. And this is done periodically, okay? So the same assumptions also for the command that you're applying to the switch. So we label the first mode to be mode number 1. All right, in this mode, the switch is on. We turn it on, no surprises. And the duration of this mode is from 0 all the way down to the duty cycle times period. Okay. So similar to before, what we have to do is find out what happens to the diode. Is it on or is it off? So we have to make an argument about that. All right, so let's do that. So if you turn the switch on, so what's happening is, let me draw the system over here. All right, so on the primary side, this is what the system looks like. There are two things happening. One, you're applying your input voltage across this magnetizing inductor. So the magnetizing inductor current is going to rise, similar to before. When you had an inductor in the first mode, the current rises. At the same time, you're applying your input voltage across the primary side of your transformer. And you can reflect that and see what kind of a voltage appears on the secondary side of the transformer. So if this voltage is labeled to be V1, V of the primary side and the secondary side is V2, so V1 equals to Vn. So the input voltage is applied across the primary side of the transformer. At the same time, because this is an ideal transformer, we already know that V1 over V2 equals N1 over N2. So remember, there is a secondary side over here. The dot is here in the bottom. Therefore, V2 is basically in this polarity. All right? All right. So you know this general equation that holds for all transformers. Then you are applying V1 to the Vin to the primary side. So you can find V2, which is the reflection of the input voltage, like N2 over N1 times Vn. By the way, obviously, N1 is the number of turns here, N2 is the number of turns here, and some people emphasize on the fact that there is a core in between. Okay, all right. So we know V2, all right? Now we can actually take a look and see what is happening to the diode. Okay. First of all, I'm making this assumption that V out is in this polarity. Then later on, if I realize that it is not and a negative sign appears in the equation, then I have to go ahead and change that. But this is the right assumption, actually. Okay, so I have V2, I have V out. I can apply KVL over here and see how much of a voltage I am actually applying across this diode. Is it positive? Is it negative? What's happening? All right. And this is the equation over here. The voltage across the diode is negative V2, negative V out. For V2, I'm going to replace N2 over N1 times Vn, and you can see the whole thing is negative, assuming that V out is also positive, and later we are going to confirm that. So you can see this whole thing is negative. So you can argue that, okay, I have a diode, and by turning the switch on, a negative voltage is applied across this diode. Therefore, the diode is off. So no surprises. Similar to before, as soon as you turn the switch on, your diode is reverse biased and off basically. Okay. So nothing much is going on the secondary side of the transformer except for the fact that this capacitor is being charged through the load. So the capacitor charge is going to go down. But on the primary side, you're kind of energizing the system. You're energizing the magnetizing inductance of the transformer. Okay, so let's take a look at that. All right, so this is the circuit that I just drew on the right-hand side. I know that because the diode is off, there is no current. Remember, if you only have two windings, the primary side current flows into the dotted node, and the secondary side current flows out of the dotted node. So this is I2 basically. Okay. Now, because that diode is off, that means there is no action going on in this loop. Okay? That means I2 is 0 basically. Okay, if I2 is 0, that means I1 is 0 because I1 and I2 are proportional with each other. Remember, I2 over I1 is N1 over N2. So if I2 is 0, the conclusion is I1 is also 0. Okay? All right. So I1 is 0. So that means this ideal transformer that I have, that is kind of representing my real transformer. In that ideal part, nothing is really going on. The only thing that is happening is we are applying this Vn across this magnetizing inductance. Okay? So VLM, which is the voltage across the magnetizing inductance, is the same as the input voltage. For any inductor, the voltage of an inductor is the value of the inductor times the derivative of its current. So you can easily write an equation for the magnetizing inductor current. So it starts from some, and by the way, this is in continuous conduction mode, so it is starting at some minimum value and just ramping up. Okay, ILM, which is this current. All right? All right. And by the way, this is the way we model the system. So if you really look at the system, it's sitting on the table, you can't really see LM. LM and the primary side are basically the same thing. So you cannot independently measure ILM. So please remember that. ILM is like a fictional thing that we are trying to model the system with. So all you can measure, if you really have this system sitting on this table, all you can measure is this current and this current. Okay? Okay. Similar to before, as soon as we find the equation for the inductor current, or in this case the magnetizing inductor current, we can find how much it is going to rise. So we label at the end to be I max. Then I max is basically this expression, which is I min plus the rise in the inductor current, which is the slope times duration. The slope is voltage over the value of the inductor, which is V over L, and the duration is duty cycle times period. So you can easily find delta ILM. Which is V over LM times dt. Okay? So one reason to find delta ILM is, for instance, we want to see the voltage transfer ratio of the system. We can find delta ILM in this mode. You can find delta ILM in the second mode. They should be the same, and it gives you a voltage transfer ratio. And then later on, for instance, you're interested in delta ILM because then you can say on average, I don't know, average value minus half of delta ILM is I min, and go after the continuous conduction mode criteria. All right. So this was all about mode 1. Kind of like the buck boost topology. You just turn the switch on, and the inductor gets energized and ramps up with an input voltage, with a voltage of Vn. All right. Now mode 2 starts. And mode 2 is when we turn the switch off. Okay? So this would be our mode 2. So we turn the switch off, we have to find out what is happening to the diode again. So the duration of this mode is from duty cycle times period all the way to the end of the switching period. And we want to find out what happens to the inductor, to the diode. Okay. So what's happening now is all of a sudden I have blocked this path of conduction. All right. Well, let me redraw this figure. Okay, let me redraw it. So I have this state in mind and then say, okay, all of a sudden I am blocking this current to flow through the switch. Okay, so what happens is the inductor current has to be continuous, so it finds another way to flow through, which was the primary side of the transformer. So when you open up the switch, the inductor has to find another path to basically pushes its current to be continuous, and the only path is this primary side. So now you can see that current is coming out of the primary side, out of the dotted node. Therefore, the other current should go into the dotted node. Okay? And that means if we have some non-zero current flowing into this, it's going to push this diode to turn on. So the diode is going to turn on. Okay. Similar to before, as soon as we turn the switch off, the inductor pushes the diode to turn on. Okay. Same mechanism like the buck or boost or buck boost. All right. So I have a bunch of equations kind of explaining this. So switch is off, the source current is 0 because this is the source current, and therefore the only thing that remains is I1 and I2. So remember, I1 was labeled to go into the dotted node and I2 was labeled to be coming out of the dotted node. So obviously here they are both negative because the real currents are in the opposite directions. So I1 is carrying the inductor current in the reverse polarity, and we already know I1 over I2 is N2 over N1 or vice versa. Therefore I can find I2 to be negative of N1 over N2 over ILM. That means the current is in the opposite direction, like the blue direction that I have over here. The real current is in this direction, and that pushes the diode to be on because diode is actually supporting the circulation of current in that direction. Okay, so diode turns on. All right, so now we know in the second mode, no surprises, the diode is on. So now we have to write a bunch of other equations to, for instance, describe what happens to the magnetizing inductor current in this mode. Okay. So if you look, having the diode on, basically what's happening is it is as if you are applying the output voltage across the secondary side of your transformer. You can translate it to the primary side and write a bunch of equations. So now I'm just looking at this. I can say V2, which is the voltage of the primary side, and unfortunately I have actually, hold on a second, let me see. This polarity is not correct. This is the right polarity. This figure is a little bit, okay, oops. Remember, for transformers, you always say the dotted node is the positive voltage terminal and the undotted one is the negative one. So you can see, if you look at V2 in this polarity, it is negative of V out. Ideal transformer, I can translate and see what happens to the primary side because I already have this equation. So I can find the voltage that appears across the primary side, which is the negative of N1 over N2 times the output voltage. And whatever is on the primary side, it is actually our inductor voltage because they are basically in parallel with each other. So if you look at this voltage, it's the same as this voltage. All right. So you can see in the first mode we were applying Vn across the magnetizing inductor. Over here we are applying a negative voltage, which is the reflection of the output voltage. So if you want to draw this, it would be something like this. in the first mode, the primary side voltage, which was VLM as well, was Vn. Here it is negative N1 over N2 times Vout. If you look at this, this looks a lot like the buck-boost topology. The only difference is an N1 over N2 appears in the equations. Otherwise, they are basically the same. So I haven't done this delta ILM in this mode, but you can do that. You can argue that, okay, the inductor current is falling now, and you can find another delta ILM based on this mode, and then compare the first delta ILM versus the second delta ILM to basically find the voltage transfer ratio. Or there's always a simpler way, and that is arguing that on average this VLM should be 0, so these two areas should be the same, or Vn times dt, which is the area of that this square over here, is the same as the area of this square, which is N1 over N2 times Vout times 1 minus d times t. So in the end, you will end up having this voltage transfer ratio. Vout over Vn is d over 1 minus d, so far similar to the buck-boost topology, times N2 over N1. It's like you're combining a transformer and a buck-boost topology together, okay? So this is our voltage transfer ratio. So this is for the flyback under CCM. All right. Now, if you go back to your 205 background information, we were not allowed to apply, we were only allowed to apply a sinusoidal signal to the primary side or the secondary side of a transformer. Here we are not. We are actually applying a DC kind of a voltage. So you may argue that, oh, wait a minute, how come you're using these equations? Because these equations only hold if your signals are AC. But as it turns out, our signals are not sinusoidal, but they are AC. Because if you look at the primary side voltage of the transformer, it is not a sinusoidal signal. It has two DC levels, but on average it's 0. So you're not really doing anything illegal, okay? Remember, anytime that you have a transformer, you got to make sure the voltage that you apply to the primary side or the secondary side of that transformer, on average, that voltage should be 0. And here we are exactly doing the same thing. On average, this voltage is 0. So even though our voltage waveform on the primary side, this is basically V2 times N1 over N2. So you can see the primary and secondary side voltages are not sinusoidal. They're kind of a square shaped, but on average they are 0, so no problem there. All right. So bunch of waveforms over here. Let's take a look at them. Let me just make it a little larger. Yeah, that's good. So this is our switching pattern. We turn the switch on during the first mode, the initial mode of the switching period, and then turn it off. So this is one period, and this is the second period over here, and this is DT. Okay? On, off, something like that. We just saw in the first mode, so this is V on, which is the same as VLM, which is N1 over N2 times V2. In the first mode, it's positive. It's actually Vn. In the second mode, it's negative. It's the negative of N1 over N2 times Vout. And this is periodically being repeated. Okay? Positive constant voltage applied across the terminals of an inductor causes a kind of a ramp in the inductor current, positive ramp, and then negative ramp, then positive ramp, and then negative ramp. And this is between Imax and Imin. I1, which is this current, this imaginary current that you can never ever measure, this current over here, the current that goes into the primary side of the ideal transformer. Okay, so let's draw that. In the first mode, remember the switch was on, the diode was off, therefore I2 was 0, therefore I1 was 0, so this is 0. In the second mode, I1 was the same as the magnetizing inductor current, only in the opposite direction. So whatever I have up here, I have to just draw it over here with a negative polarity. So this starts from negative I max, then goes up to negative I min. All right, something like this. What about the current of the diode? Remember, in the first mode, the diode was off. In the second mode, the diode was conducting obviously some positive current, and that was the reflection of the inductor current from the primary side. And since this is a reflection, on the primary side, we have I max, but I max has to be translated to the secondary side, so this would be N1 over N2 times I max. And similarly, this negative value is N1 over N2 times I min. What about the input current or the switch current, which is the sum of the magnetizing current and the primary side current? So if you're looking at this input current over here, you should basically look at this current and then add it with this current. Okay, and we have both of them. We have I1 over here. All I have to do is just add it with ILM to find the input current. So in the first mode, we have non-zero current going on, an indication that you are using your source to charge the system. In the second mode, nothing is going on, and this also looks like the input current of the buck boost topology. All right, it's discontinuous, unfortunately, and that's one of the disadvantages of the flyback converter. Now, when it comes to selecting the switch, you want to see how much voltage is applied across your switch. Okay, when it is off. So we should take a look at that. In the first mode, the switch is on, so no voltage drop. Okay. In the second mode, the switch is off, but we have all the voltage information. So basically, in order to find this voltage, all I have to do is take a look at KVL around this loop. Okay. So this gives me the voltage of the switch is the input voltage minus V1, okay, if this is V1. Okay, and V1 by itself is negative, which was the N1 over N2 negative, N1 over N2 times V outs. We had it here actually, okay. So if you just replace it, it would be voltage of the switch is Vn plus N1 over N2 times V out, okay? So when the switch is off, obviously it should be blocking some positive voltage, and this is the value of that positive voltage. All right, so this gives me this level over here, okay? All right. And you can again write V out as in terms of Vn, because V out is N2 over N1 times D over 1 minus D times Vn. So if you just do everything, you're going to end up something like this. This is the amount of voltage drop across your switch when your switch is off. Okay. What about the voltage drop across the diode? I have it up there, but I'm just going to read it right down here. Well, first of all, in the second mode, the diode is off, so it's very easy to draw this 0 part here and 0 part here. However, in the first mode, we actually found the diode voltage, which was a negative thing. That's how we concluded that the diode was off. Oops. Here it was. The diode voltage is negative N2 over N1 times V and negative V out. So it's a negative thing. And I have it actually written over here. I'm not going to rewrite it. I'm just going to draw it. let me write it. It's negative N2 over N1 times Vn negative Vout minus Vout. So you can see how much of voltage stress you have applied across your switch and your diode, and that leads you on how to basically pick these components from the available products out there. One thing that I forgot to mention was when we were in the first mode, when we were making this argument about the diode voltage, I assumed Vout was positive, the polarity that I had selected was positive, and that turned out to be a correct assumption because you can see there is no negative sign appearing over here. So that initial polarity that I chose for Vout was the right one. And here we have double, checking that. All right. So when it comes to the continuous conduction mode, in order to guarantee that the converter is operating under continuous conduction mode, you have to find Imin and then make sure Imin is positive, and that gives you an equation for picking up the right size for the inductor. Now we are not doing any the details over here. The details are very similar to the buck boost topology. The only difference over here is there is an N1 over N2 or N2 over N1 thing appearing over here. But anyway, here I have it. The minimum value of the inductor current. This inductor is the magnetizing inductor reflected on the primary side. Is the average value minus half of its ripple. The average is Vn over R times N1 over N2 squared times D over 1 minus D squared. So before, for buck boost, we didn't have this part. The rest is exactly the same as the buck boost topology. Then minus half of the ripple, and the ripple is Vn over 2 over Lm times the duration of the first mode, which is the duty cycle times period. And obviously for the maximum value of the inductor current, this turns out just in the polarity changes to a positive signal basically. So everything is very similar to the buck boost. So if you want to make sure that your inductor you're operating under a continuous conduction mode, you got to make sure that your inductor is greater than the magnetizing inductance of your transform is greater than this expression. And if you compare it against buck boost, it's exactly the same thing, only N1 over N2 squared appears here. And again, the same trend. The frequency appears in the denominator. So if you increase the switching frequency, you will need a smaller magnetizing inductance. For the cap voltage, because everything is reflected to the output side, the N1 and N2 do not even appear. It's exactly like the buck boost topology. So you got to make sure your C is larger than D over R times frequency times delta VL over VL. Okay. So these are the design equations. All right. So we didn't go through details because I'm sure by now you're very familiar with. One other thing that, by the way, I forgot to mention, similar to 205, remember we can always reflect this magnetizing inductance to the secondary side. Okay, so it doesn't really matter where you assume the magnetizing inductor is. It could be on this primary side, it could be on the secondary side, or it could be split between the primary and secondary. It doesn't really make a difference into the analysis. But it's usually we are used to, reflecting things on the primary side. So most of the times your magnetizing inductor is assumed to be on the primary side, but that doesn't really make a difference. You can assume it's on the secondary side, or you can say it's a split between the primary and secondary sides. Okay, any questions? Yes?
Like the voltage across the diode, when we are seeing in the single phase rectifier for the center tap one,
okay,
even there like it was 2 times the output voltage.
Okay.
So
or 2 times the turns ratio or something like that. All right. Okay.
So whenever we use a isolation transformer, so it will be stressed
well, in that particular topology, you're right, because in that particular topology, in the full wave rectifier with a center tap inductor, you are trying to avoid using 4 diodes and only use 2 diodes. Therefore, the voltage stress across those 2 diodes is doubled. So you're kind of tricking over here. That is not really comparable over here because in this topology you're only using 1 diode. So this the voltage that we calculated is stressed over this one particular diode. So it's, that comparison, we are going to see topologies like that later, that we have actually 2 diodes on the output side and looking at the voltage stress over here. But over here the equation that we have is, you can't really say it's better than that or less, different, less than that. It's just different than that, okay? The stress on the voltage of the diode. All right, any other questions? Yes?
Now we know that the resistance of the load affects the continuity of the current.
Okay.
So if the load varies and we want the output to be continuous.
Continuous, you mean the converter? Okay, the question is how should we incorporate the changes in the load in our equations to make sure that it is operating under continuous conduction mode, right? So similar to before, whenever you have these inequality signs, you got to find the maximum value over here and then make sure L is even larger than the maximum value. So here it's very easy. You have to consider the maximum value of your load. Okay? So if your load is variable between like 20 to 50 ohms, you should consider 50 ohms to guarantee that your system is operating under continuous conduction mode. Other questions?
Dr. Ferdowsi, like in the first mode, I source is equal to the ILM.
Right.
So, like, can we measure the ILM by measuring I source?
That is a good point. Yes, we can. Having the knowledge of in the second mode, it's something actually different. You can actually you can argue that, okay, let me look at these waveforms. So we have IS, which is the current of the source. We can easily measure it. Okay? And then we will have a waveform like this, and you can say, okay, I've measured this, so I can conclude that, for instance, I1 looks like, because if you have one of them, the important information about this is the minimum and maximum value. So while you have measured these, you can actually construct the rest of the waveforms. Yes. So yes, you can play tricks, and sometimes actually this is a trick that you use, for instance, for peak current mode control. You have to look at the peak value of your magnetizing inductor current, but this magnetizing inductor current is really almost impossible to measure, because it's not a real inductor. It's like embedded with a bunch of other components. So what you do is, you basically need this information for the peak value of your inductor current, but you can measure the switch current and find the same peak value information. So yeah, you can do that. All right, other questions? Okay, so no questions. So let's take a look at, I guess we have 2 examples. All right, the first one is relatively easy. We have this, we are supposed to, for instance, consider this flyback topology that we just analyzed, and the input voltage is 20 volts, the output voltage is 5, and the output power is variable between 1 watt to 10 watts. And the number of turns has already been selected, and 1 over N2 should be 3. So it's like a step down kind of a transformer, because number of turns on the primary side is higher. And the magnetizing inductor on the primary side has been measured to be 500 microhenries. And then the question is, okay, we have already designed this, but we haven't told you what is the frequency that this thing has to operate. The question is, find a frequency range at which the converter operates under continuous conduction mode. All right. Before getting to the example, let me mention something else that I forgot. Sorry about switching back and forth. Another good thing about this topology is you can have several outputs. So you can actually, for instance, for your senior design project, you are trying to have a 5 volt and a negative 5 volts, and 15 volt plus or minus 15 volts, things like that. So you need to have bunch of basically voltage levels for the the analog circuitry that you're using. So you can actually do that, achieve that using this flyback topology. All right, let me draw it over here. So basically you can have multiple outputs. The primary side doesn't change. But you can have actually two outputs. All right. All right, so this could be one of your outputs, and the second one could be here. And the good thing is these outputs don't have to have the same common ground. They can actually be isolated from each other. So by selecting N1, N2, and N3, for instance, if you want 5 volts on the N1 on 2 side and 15 volts on the N3 side, obviously the number of turns of N3 should be 3 times N2, okay? So you can have actually multiple outputs at the same time. So this is another advantage of this isolation that appears in the flyback topology. All right, so going back to our example, all right. So first of all, the range of the output power is provided. What we can do is to find the range of the load resistance, because we actually have the value of the output voltage, which is 5 volts. So we know that the output power is variable from 1 to 10 watts. The output voltage is 5 volts, and it's a DC system. Therefore, the output power is V out squared over R. So do some math, and you realize that if the power is supposed to be variable from 1 to 10 watts, that's the indication that the load resistance is variable from 2.5 ohms to 25 ohms. All right, so that's easy. All right, the other thing is most of the times you need to have the value of the duty cycle. Well, the input voltage is given, the output voltage is given, the turns ratio is given. So looking at this equation that relates all of these parameters with each other, the only missing piece is the duty cycle. So you can easily find it, and it turns out to be 38.5%. All right. So you have the range for your load, you have the duty cycle. So ultimately we want to use this equation. Okay, turns ratio appears, we have it. R max appears, we just found it. Duty cycle, we found it. L, we have it. The only thing that we don't have is actually our frequency. All right. So remember, our requirement was for this converter to operate under continuous conduction mode. Therefore, the magnetizing inductance should be larger than this. And because our load is a variable load, we have to consider the maximum value of the load resistance. And then I just rearrange this so that the frequency should be larger than the rest of the other parameters. And it turns out that you have to select the switching frequency that is larger than about 85 kilohertz. So below the switching frequency, because your magnetizing inductance is not too large, you are going to basically face the discontinuous conduction mode. And beyond that, you're good. You can actually do continuous conduction mode. I thought we had 2 examples, but I only have 1. Let me see if something is missing here. Okay, I have actually 2 examples for the forward converter. That's probably why. Okay. But it's very easy to confuse the students with designing such a converter, because we have like an extra parameter, and that is N1 over N2. And ideally you would say, oh, it's great. So what I can do is increase N1 over N2, or I'm sorry, N2 over N1 to have a very large output voltage. But as it turns out, for instance, in that case, see N2 over N1, if you select N2 over N1 to be very large, so that you would create a very large output voltage, then you realize that the stress on your diode is also growing. So that means you have to buy a more expensive diode, and also the conduction losses in that diode is going to basically increase because its internal forward voltage drop is going to increase. So, you know, it's not like increasing some parameter is always give you a benefit. There is always a trade-off involved. And similar to the selecting the duty cycles, you can say, okay, I'm going to select a smaller duty cycle to give me a larger output voltage, but at the same time you see that that would increase the stress on your switch. So these trade-offs exist, so please pay attention to them. All right. So this was all about the flyback topology, and the good news is we don't even analyze this under discontinuous conduction mode, although there are applications for the flyback topology, and like in a power factor correction application, you might use a flyback converter under discontinuous conduction mode, but here we don't do that. The equations are very similar to the buck boost topology that we didn't analyze either, so for some reason, there is always buck boost is in a disadvantage over here because nobody is interested in analyzing it. All right, so let's move on to the next topology. This one is called the forward topology. Okay. So here's the circuit diagram. As you can see, we have this transformer over here. By the way, I'm trying to use as much red as I can today because of the game yesterday. Cardinals won, so we're using red a lot today. So there is a magnetized, there is a transformer, and this transformer has 3 windings. Okay. So let me make these figures a little larger, or actually read right over here. So we have this, let's say, magnetic core, and then we have this number 1 winding, and I place the dot over here, so immediately I have to follow this voltage polarity and this direction for this current. Okay, so that was the primary side winding. Then I have a secondary side winding, and unlike the flyback converter, the dotted node is above. And again, as soon as you assume that this is your, or find out that this is your dotted node, depending on the layout of your windings, this would be with V2. And because now I have 3 windings, I'm assuming all of these currents are flowing into the dotted nodes. So this is I2. And there's a third winding. And this third winding is wound in a way that the dotted node appears over here. So immediately I have to assume this is V3. And the current flows into. So whenever you have more than 2 windings, you always have to assume all of the, you don't have to, it's easier to assume that all of the currents are flowing into the dotted nodes of the transformer. Okay. Now the magnetizing inductance, it's up to me. I can assume it's anywhere that I want, on the primary side, secondary side, or the third side. It's just more convenient to assume it's over here. All right. And then it's up to me. I have, freedom over here. I can assume this is the direction of this current. All right. Now you can build up the rest of the system around it. Here you have your, for instance, switch, which is an IGBT. And then your source is connected here. And on the output side, we have actually 2 diodes. It's really to all right, something like this. And as it turns out, if you look to the right-hand side, what you see looks a lot like the boost topology, okay? It's just a diode and an inductor, a capacitor, and a load. And as it turns out, this is actually an isolated buck converter. I'm sorry. It looks a lot like a buck converter, and as it turns out, this is an isolated buck converter. So the voltage transfer ratio looks a lot like the buck topology. Okay, for the third winding, we don't really need this third winding. The reason that we are putting it over there is to demagnetize the magnetizing inductance of the transformer. So this is an example that you have your main inductor in the system, okay? You already have a dedicated inductor visibly. You can actually point it out in your system. So this magnetizing inductance is not really playing an important role, unlike the flyback converter. In the flyback converter, this magnetizing inductor was the main inductor in the system. Over here, it is not the main inductor in the system. It is not playing an important role, but we have to make sure it is demagnetized. Otherwise, its current is going to keep increasing to infinity. So, or in other words, you have to make sure, on average, the voltage that you are applying across the terminals of any of your windings of your transformer is 0. For that reason, we are adding this third winding and this third diode, and this is connected like this. And we are going to see how it works. So the third winding, the purpose is, because the magnetizing inductance is there, the job is just to demagnetize that magnetizing inductor. So these diodes are labeled to be D1, D2, D3. And let's say this is your switch. We only have one switch. And obviously the number of turns are N1, N2, N3. All right. And we are going to go ahead and analyze this converter. Similar to before, we are assuming that our period starts when the switch is turned on. So if you look at the gate command applied to your switch, it's on at the beginning of the cycle, then off for the remaining of the cycle. And the on period or on segment is called duty cycle times period. So this is going to be our second mode. This is our first mode, and here we have off. Okay. Okay. So as you can see, this converter, if you compare it against the Bach topology, has the same components. In addition, you're using a transformer or a coupled inductor. All right. So let's look at the first mode. So obviously in the first mode, we have turned the switch on. And this is the duration of the first mode. So whenever you turn the switch on, you're applying some voltage across the primary side of your transformer. And that is Vn. Here it is. When this switch is on, if you look at this, okay. Let me just do it a little cleaner. So if this switch is on or shorted, if you look at this loop, which is closed now, you're going to realize that you're applying the input voltage across the winding number 1, basically. All right, which is V1. So V1 and Vn are the same. And that's what we have over here. V1 is the same as Vn. Okay. Now, a transformer with 3 windings, V1 over N1 is the same as V2 over N2, is the same as V3 over N3. So we know this general equation. Therefore, we can find V2 and we can also find V3. Okay? Let's talk about V3, for instance. Now that we have found V3, that means I know how much voltage appears here. Okay? Now I can look at this loop. I'm trying to make a decision for D3 and see if this D3 is on or off. So I can actually take a look at this loop. It's a little bit of a twisted loop. Okay? So D3 and V3 and Vn are forming a loop. If you apply KVL, you're going to realize the voltage drop across the diode is negative V3 and negative V1. And please remember, we are talking about this polarity. All right? So instantly you can argue that as soon as I turn the switch on, D3 is off. Very good. So that's one conclusion. So D3 is definitely off. For the other two diodes, it's a little bit more complicated. I don't think we have time to cover that. So right now I know that we have 3 diodes. So for each one, we have to basically make a decision or find out which one is on, which one is off. For now, we have realized that as soon as I turn the switch on, D3 will be reverse biased. What happens to D1 and D2, we are going to talk about it next time. But as it turns out, D1 is on and D2 is off, kind of like the buck converter when this diode is off when you turn the switch on. It's pretty much the same mechanism over here. All right. So I'll see you guys next week on Tuesday. Please don't forget about the quiz covering the buck boost and buck boost topologies operating under continuous and discontinuous conduction modes. The sign-up sheet is circulating around. If you were late, don't forget to sign it.
బౌండరీ కండిషన్స్ కన్సిడర్ చేయాలి కదా నాకు అదొక్కటే డౌట్